welcome to Innovate and React. In today's episode, we will be talking about sustainable ammonia synthesis and what we can do with it. And my guest today is Kevin Rouwenhorst, and he is the technology manager at the Ammonia Energy Association. Welcome, Kevin.
Thank you, Kevin. Nice to be here.
Yeah, I saw your post on LinkedIn regarding your book about ammonia, and I got very interested in learning about this. So what made you look into ammonia and write a book about it?
Well, I can tell a very nice story about that I always wanted to go into ammonia, but it has kind of evolved over time. So initially I was studying chemical engineering at the University of Twente, doing the master's, and then I was looking for an internship, and I kind of knew that I wanted to be in the more or less clean fuel space or clean molecule space, preferably like the smaller molecules like ammonia, methanol, and that was back in 2017. So you can imagine that's like very early stages. So not like today where there's actual projects that are ongoing. And I remember that back then there was this George Ola project in Iceland on methanol, the CO2 to methanol, which was quite interesting. But also I already saw some interesting items about ammonia. So then I was applying for internships, and I got a position at Halder Topsoe in Denmark. Nowadays the company is called Topsoe. And they said that I would be doing something with small molecules, so syngas conversions. It could be either methanol, could be ammonia. And then actually, I did my internship there, worked on ammonia synthesis catalysts. For confidentiality reasons, I cannot tell you exactly what I did, but I worked on some ammonia synthesis catalysts. And then I started just Googling sometimes about ammonia because, of course, it was also relatively new to me. And then I found this organization called the NH3 Fuel Association, nowadays the Ammonia Energy Association. And then I started reading up on the conferences, all the presentations, and I found out that ammonia could be a fuel for the future, a zero carbon fuel. And I thought that's quite interesting. So then I decided to do my master thesis about this topic. So making kind of a decentralized ammonia system for energy storage. So you have some solar, some wind, maybe some batteries for the short term, and then longer term electricity storage you could do in the form of ammonia, so chemical energy storage. When then you need the electricity in the winter, when the sun doesn't shine so brightly, maybe you have a Dunkelflaute, as you call it so nicely in Germany, and then there is no wind for a week, and that's the moment where you need the heating. And if in the future you're going to electrify your heating, well, that's when you need probably the ammonia.
So actually ammonia also for the energy production, that you directly use ammonia in some power plant, for example.
That's exactly correct. So back in the day when it was quite academic, so I opted for this kind of reversible solid oxide fuel cell that could on one hand make my hydrogen, but then when I need to convert my ammonia back to electricity, I would use the fuel cell functionality.
Interesting.
That's where it all started, and then I found this PhD position on plasma catalytic ammonia synthesis. And on one hand, I really wanted to dive a bit deeper into catalyst development, novel ammonia production technologies. But I also felt that back when I started 2018, it was quite early days. So what I found is that even though I really believed in the topic, it was quite early days. So during my PhD, I actually noticed that the interest in ammonia really grew over time. And around 2020, I would say that's kind of the tipping point where it became quite mainstream. So before it was quite a fringe kind of topic. So this NH3 Fuel Association that I mentioned before, it was part of a conference called the IKE annual meeting. So that's like a kind of a chemical engineering conference for academics in the US. And it's like a very big conference, and it would be one room, one afternoon basically spent on this topic for the NH3 Fuel Association. Just maybe maximum 50 people in the room if you're very lucky. But what actually happened is that over time, this became really part of the conversation. And that's also where, it became quite interesting. And I got in touch with a lot of the people who were already involved in the topic. So both from the academic side and from the from the industrial side and from the association side. And then back in 2020, I got this, 2021 actually, I got this invitation to write this report for IRENA. It's called Innovation Outlook Renewable Ammonia. And with the publication of that, that's around the time where it really became big and mainstream. It was also really the hype cycle, I would say, for the hydrogen. Everybody wanted an electrolyzer in their backyard, and these were going to be exceptionally cheap. So back then, the predictions were there was going to be renewable or green hydrogen everywhere, and the logical part of that would be ammonia, because 1/3 of the hydrogen today goes to ammonia. So it makes a lot of sense to then also talk about ammonia. A few years later, a lot of developments have happened, and what I actually saw is that there's a lot of academic work, there's a lot of developments in industry, but there's not really anything like combining the two. So what I decided is I'm going to write a book on the topic, and I really tried from a chemical engineering point of view, like these older handbooks that you have on certain topics, like chemical technology, for example, to really do that for low emission ammonia technologies. So it means decarbonized ammonia production, but then also the infrastructure to store ammonia, to transport ammonia, and then also ammonia utilization for hydrogen production again, if you want to do that, but also direct use of ammonia as a fuel for either power generation, the maritime sector, or for example, for heat. And of course, because I'm still a little bit of an academic, there's also one chapter of any other technologies that might apply to ammonia in the future, like these novel electrochemical ammonia synthesis technologies, or even ammonia to steel, like all these new technologies as well.
Very interesting. So that gives really a round trip, like from the whole ecosystem, production, utilization, everything in there, but with the focus on low emission ammonia. So maybe to differentiate it from the normal ammonia, I would say it nowadays, it's still mainly with the conventional Haber-Bosch process. There was also a previous episode about the Haber-Bosch process, but maybe let's shortly recap what that is and how it works.
Yes, that would be good. So when I read academic papers, quite often I get little bit irritated when I read papers about the Haber-Bosch process and then some new process where they say, well, the Haber-Bosch process, it emits a lot of CO2. Well, I do not personally believe that. And let me explain a bit how I see the process. So when people talk about the Haber-Bosch process, they're typically in these academic papers, they integrate the hydrogen production, the nitrogen production, and the ammonia production. Whereas if you very principally look at the process, the Haber-Bosch would refer to the ammonia synthesis loop and not to the hydrogen production and nitrogen production upfront. And then if you look at the emissions related to current ammonia production, so mainly it's produced either via natural gas reforming for the hydrogen or via coal gasification for the hydrogen, then more than 90% of your CO2 emissions actually come from the hydrogen production and not from the last part of your process. So when people talk about the Haber-Bosch process and then they claim it has a high carbon intensity, no, it's actually not true. It's really the hydrogen production via either steam reforming or coal gasification that gives this high CO2 emissions.
Yeah, but they are really integrated plants, right? When these large-scale Haber-Bosch process, you cannot just take out the ammonia synthesis and like it's interconnected with all the heat transfer and the use of all the side streams, I guess.
I mean, it's very similar to any industrial site where if there's steam available, you might want to use it for a compressor or for some other utilization. So there's always this interconnection, but it doesn't mean that fundamentally you would need to do that. So of course, it's going to cost you money if you want to change that. But for example, what you could do is right now there's high pressure or medium pressure steam that comes from the steam reformer section for the hydrogen production. And that's then also being used to generate like the power or the energy for the compressors. You could electrify your compressors if you don't have that front end. It's going to cost you quite some money, but you could technically do that. So you could actually decouple the front end and the back end. It is just more of an investment item. The other thing that I would say is still, of course, they're interconnected, but we should not get out of our sight that the hydrogen portion is still more than
Yeah.
90% of your energy and thus CO2 emissions. So if we're kind of keeping them in an equal discussion is not fair, because like on one hand you have all this natural gas going in, on the other end you just have like some waste steam streams that are coming in.
Yeah, exactly. And then with the hydrogen, you combine it with nitrogen, and then you get ammonia out of the reactor. Where does the nitrogen come from? That's usually air liquefaction, right?
No, there's multiple ways to do it. So typically, what happens is that for a gas-based ammonia plant, so if you have a steam reforming there, actually what is designed for an ammonia plant is that the primary reformer is more like a tubular steam methane reformer, where basically hydrogen is produced together with carbon monoxide and carbon dioxide from the reaction between methane, so natural gas, and steam, using some burners external to the pipes. And then there is a secondary reformer, which is basically a small-scale autothermal reformer, but rather than firing this with oxygen, which is the normal way to do it, it's fired with air. So you kind of introduce the nitrogen that you would need next to the hydrogen for the ammonia synthesis. So that's one way to do it, and this process operates somewhere around, let's say, 30 bar. And then you would still need to compress the hydrogen nitrogen to the pressure of the Haber-Bosch loop, like 100 up to maybe 400 bar, depending a bit on the plant configuration. And so that would be one way to do it. The other way, what you already mentioned, is indeed air liquefaction. So a cryogenic air separation unit would be the way to go. And if you look at decarbonized ammonia production, either via autothermal reforming, so instead of having like a two-phase process, but now you just have like one big autothermal reformer, maybe with the pre-reformer. In that case, you would fire the autothermal reformer with oxygen and then separately supply the nitrogen to the ammonia loop. Similarly, if you're talking about the renewable ammonia production, so basically with an electrolyzer for the hydrogen, then you would also have this air separation unit and you supply the nitrogen. In this case, you have a lot of surplus oxygen that you're not necessarily using in all cases.
Yeah, but that can be maybe used somewhere else. This would be the conventional process. And you already mentioned that most of the CO2 emissions actually come from the hydrogen production. So when we come to the low emission ammonia, now I think that means basically trying to produce the hydrogen somehow else. Or how does it differentiate?
I mean, to a large degree, you're totally correct. Most of the emissions come from the hydrogen. So it's mainly a narrative of how do we decarbonize the hydrogen production, and then also how do we integrate that then with this process, so this Haber-Bosch process. How do we get this ammonia synthesis loop to also be adequate for these conditions? Because you can imagine that if you're decarbonizing a gas reforming technology, basically that's still a baseload hydrogen output. Whereas if you look at an electrolyzer, for example, if you're going to couple it with solar and wind directly and it's going to be flexible, you will have to think a bit about either having a hydrogen storage buffer or having like a more flexible ammonia synthesis loop. The combination is in both of them to optimize the cost and also safety wise. But that's really the challenge. How do we decarbonize the front end, the hydrogen, for the ammonia production?
And what are the main challenges with this? You mentioned the flexibility of the ammonia synthesis loop. What else is there?
I would say that the biggest challenge here is cost. So if you look at most of the ammonia industry, and by the way, that's around 200 million tons of ammonia production
Which is
worldwide.
very
So
large.
that's very significant. Most like 55% of this ammonia is also integrated with urea production, and that kind of needs the CO2 for the basically for the urea product. So relatively difficult to decarbonize that portion, maybe with some biogas, but like you also would need to scale that. That's a really big question mark. But that leaves like 45% of non-urea use, where you could already sequester part of the CO2, and that's the process CO2 that you make next to your hydrogen and your nitrogen. So you could do that. But getting back to your question regarding some of the challenges, so indeed cost. If you have the existing ammonia plants, they're basically already amortized. So they are old plants typically in many locations. So you don't pay for any capex except for some maintenance and some upgrading of your plant, but you just pay for the gas feedstock, and natural gas is still a relatively cheap feedstock. But then decarbonizing via the two main pathways, so via renewables plus electrolyzers or via CO2 sequestration, has two kind of challenges. So let me first go to the one that is for electrolysis. So that's really the cost of electrolysis. And also it would be nice that we have some large demonstrators in multiple locations. So we already have some commercial scale plants in China producing quite sizable amounts of ammonia. So then we're talking about hundreds of megawatts of electrolyzer capacity coupled with renewables.
Okay.
And then we make something up to 300 kilotons of ammonia per year in a single plant or into two ammonia trains. So that's already there, but it's really cost. So in China, electrolyzers are relatively cheap. If you want to build an electrolyzer in Europe, it's multiple times that cost. So that also means that the cost of your renewable hydrogen, green hydrogen, as some people call it, becomes really high, and that then also is translated into the ammonia. And then the question is, which customer is willing to buy that premium, quite expensive renewable ammonia? So that's for the renewable ammonia portion. Then if we go to gas-based hydrogen production and then often integrated with nitrogen production, then we have two other challenges. So one challenge is if you have an existing ammonia plant, it's typically a two-stage reformer system where about 2/3 of the CO2 is produced in the process gas together with your hydrogen and nitrogen. So already captured in ammonia plants because you have to remove it before you make the ammonia in the Haber-Bosch ammonia synthesis loop. So that technology is already there, very purified CO2. But then what we see is that there's also about 1/3 of the CO2 that is produced from the burners in this primary reformer, so in the tubular reformer. And that CO2 is flue gas CO2, so it's relatively expensive to capture in these existing ammonia plants.
Okay. One question for that. When you use the hydrogen production there, we already have this carbon capture technology because for the actual synthesis, you need to purify it anyway, and there you have to do it. But what is the difference of the flue gas capture?
So the difference is the pressures are very different.
Okay.
So if you are with this kind of Eman scrubber for the process gas before the ammonia synthesis loop, that's probably at 30 bar, but flue gas is probably at much lower pressures, and therefore, I mean, partial pressures are kind of dictating how easy this separation is going to be. So for flue gas, that's much more expensive and will be an add-on on top of the existing facility.
Okay. So you have to add more pressure then to have a better separation.
You could, but then you would have to revamp the entire facility, and then the question is whether this is actually the most economic way to do it. So people also look at different solutions for gas reforming, which is like autothermal reforming or partial oxidation, depending a bit on the cleanliness of the natural gas, how many impurities there are, what is the exact configuration that makes most sense. But let's not go too deep into that today. But let's just take the example of autothermal reforming. So in that case, rather than burning your gas outside the tubes and making flue gas CO2, in this case, you put the burner inside of the reformer in an autothermal reformer. And in that case, the burner is in the same places where you make your hydrogen and your CO2 and your CO in this case, but that then gets converted into CO2 and some hydrogen. But in that case, you only make mainly purified CO2. So you have a much higher carbon capture rate already prior to your ammonia plant. So if you look into the future, most plants are based on this gas reforming with two-step reforming. Maybe they need to revamp also in part to autothermal reforming and partial oxidation. to get these higher carbon capture rates. But the second problem is actually also then you need infrastructure to sequester your CO2. That already starts at the ammonia plant. In the first case, if you make CO2, you need a processing unit that actually upgrades your CO2 a little bit more to the specs of the pipeline for the CO2. That only becomes economic once you have a relatively large pure CO2 stream. So you don't do that for the smaller ammonia plants, but typically for the larger capacities. And then you also need the CO2 infrastructure to be in place. So if you look at, for example, the US Gulf Coast already has a lot of CO2 infrastructure for enhanced oil recovery. So in that case, if there's new sites that are being discovered for geologic CCS, then it's very easy to use that existing infrastructure. But for example, in many places in Europe, there's many talks about CO2 pipelines. For example, also if you look at the Netherlands and Germany, the
Rotterdam
Delta
and
Rhine corridor, for example, there's plans for that, and also CCS sites are being developed, but there's not so many places available yet. So also that infrastructure on the CCS side needs to be upscaled.
yeah, definitely. And also storage sites have to be somewhat close. But another way would also be to use the CO2 for some chemical processes, like urea is already used. But in the future, if we want to also defossilize our chemical industry, we would also need some kind of carbon source. And there, this CO2 could also be used for chemical processes.
So I wanted to make one comment about that, and that is really about what is the source of the CO2? Where does it come from? Is it like a biogenic or is it a fossil CO2 source? And the second point to that is then what is kind of the lifetime of that CO2 in that product? Because if you make ammonia and then you make urea and you put that urea on the field 1 month later or a few months later, that CO2 will still be emitted to the atmosphere. So I would argue that that is not really a meaningful CO2 capture versus time. You could also think about other chemicals, like you could use the CO2 to make, for example, methanol then. But then again, if people want to use methanol as a fuel
Yeah.
in a vessel or convert it to SAF for aviation, well, a few months later, you also still emit that CO2. So I would not see that as a credible claim. But if you made materials that, let's say, it's not set in stone what is the exact time, but like in Europe, they also have these carbon sinks of 35 years, let's say 30 years carbon sink. That could then be, for example, be a meaningful decarbonization.
Yeah, or if you make polymers out of it, for example, then they have a much, much longer lifetime. So there the CO2 would be stored. But it's more difficult, and their costs also come into play again. If you had so many steps to make the crude material, which is really cheap nowadays, and then it's difficult to compete.
And the other issue is also from a legislation point of view, it is very complex to see where is it actually a meaningful decarbonization, and how do you grade anything in between that?
Okay, then let's go back again to the ammonia. We now talked about the low emission ammonia, so that mainly means decarbonized hydrogen production or capture the CO2 in the hydrogen production process and then store it somewhere. And when you look at the electrolyzer and the electrolytic hydrogen that you get, we already mentioned the flexibility of the ammonia plants. Such big plants usually like to run in like one operating conditions, and they don't really like to go on high load and low load. What is the research there currently? Is it there are already processes that can withstand these load changes?
So there is indeed some new plants that are being constructed to be able to do this. So it might not be all the old existing plants that would be able to do it for some of the reasons we already discussed with the steam integration. Of course, you could like make electrical motors, but the question is also at some point, if you have a very old plant in the economic reality of ammonia of Europe, whether it actually makes sense to produce all of that locally. I could also see a future where Europe does not produce all of its ammonia locally anymore, but maybe import part of the ammonia for the decarbonized products, and then maybe for the urea products where you need the CO2, it would still be co-sited in Europe, so with an ammonia plant and a hydrogen plant then. But there is indeed already a few examples where this is being demonstrated. So the example I alluded to earlier is in China. So first, the company Envision, they built a 20 kilotons per annum ammonia demonstrator. So that plant is maybe like 50 times smaller than the largest ammonia plants in the world. But it's already like quite a industrial size demonstrator. Similarly, Topsoe and Skofgard Energy in Denmark, they also have like a flexible ammonia plant now operational. And that then becomes a footprint for the NEOM project in Saudi Arabia, which is like a world scale 1.2 million tons per year ammonia plant in Saudi Arabia. So what you see is that today there are these demonstrators, and in China already scaled up versions of that, so commercial scale plants of like 100 to 300 kilotons per annum. But we need definitely a few more examples of this being successful to showcase that. But I would say this is mainly new build capacity that will do that. What you will see is that existing ammonia plants will relatively likely have some decarbonization with electrolyzers. But if you can balance that with baseload gas supply from a natural gas reformer, you do not need to have this extreme flexibility that you would need to have in a fully renewable
Okay.
ammonia
So you
plant.
basically want your constant hydrogen stream, and then you produce with the electrolyzer, and whatever is missing when the electrolyzer is going down because the renewable energy is not as available, the natural gas would produce the rest, and that can then be flexible.
Well, I don't even say that you would need to change anything on the natural gas, like that could be constant. And then you could have your renewable hydrogen being like fluctuating, because the existing ammonia plants there is not like they're totally inflexible,
Okay.
but it's just beyond a certain point that it becomes a bit tricky. And it's not only for the flexibility aspect of the ammonia loop. I think that's not the main bottleneck here. But the main bottleneck at some point is also that your nitrogen is typically fed in the secondary reformer via air. So that's for the burning the air to make the reforming happen. And if you're gonna scale down the gas supply of hydrogen from that two-step reforming process, at some point you're also not supplying enough nitrogen anymore.
Okay.
So then you also need to think about like beyond like 20-25% of decarbonization via electrolysis, do I need to build a separate air separation unit? And if I have to think about that, then the economics become all of a sudden a lot less interesting.
Yeah.
And so that's more the bottleneck for now for decarbonizing these existing ammonia plants with electrolysis.
Okay. And for the new ones, do they then also need new catalysts, and or is it mainly the engineering of the plant that you can go up and down with the input streams?
I would say the catalyst is still relatively similar. I would also add to that is that because the chemical plants always operated in the same regime, like always the similar temperatures, same hydrogen to nitrogen ratios, that these kinetic models to predict the activity of the catalyst in the reactor was always relatively narrow. And actually, the work of a PhD student that I also was involved with at the University of Twente, we made a more robust kinetic model that would also be able to predict the activity of iron-based catalysts that are typically used in ammonia synthesis plants under vastly differing conditions. So from 1 bar to 100 bar, from a hydrogen to nitrogen ratio of typically stoichiometric, so that's around 3, all the way to much lower hydrogen inputs and more nitrogen inputs. So we will be able to simulate what would happen in a turn down where your hydrogen supply is basically also going down. So I think it's more a understanding and modeling of the heat profiles kind of engineering challenge And the second thing that I would say about flexibility is really the materials. So if you're thinking about the flexible ammonia process, what basically happens is that you have some strategies to do that. So first of all, you can decrease the amount of hydrogen supply or just total supply in general, but that would decrease your pressure in your loop. Like if you're supplying less to the loop, then maybe your pressure goes from 150 bar to 100 bar. But the second thing you can do is to have a surplus of nitrogen in the loop. So the amount of hydrogen that is basically lacking because you're decreasing the amount of hydrogen via the renewable electrolytic production, and you basically oversupply the nitrogen. So in that case, you make sure that the flow in the ammonia loop still stays relatively constant.
And the pressure,
but your pressure,
that the pressure stays constant, and the stress,
the expansion, kind of like the stress and the on the material. So it doesn't stay entirely constant. So you would still have like a pressure drop that's quite significant. But what the licensors for the ammonia loops typically say is that they feel quite comfortable with going down to 20% of the production capacity. But going down to 10% of the production capacity is something that should be more sporadic, maybe once per day or even less, because that is really the moment where this pressure drop and this material fatigue becomes an issue. The one thing I would also like to stress here is when we talk about the load, about the production capacity, we can go down to 10 or 20% of the load. What we're then really talking about is how much ammonia do you produce from your ammonia loop. But it doesn't mean that the utilities and the power consumption of your ammonia loop are also at that level. Because at some point below, let's say, 50% of load, your compressor cannot turn down further. So even if you're at 10% load for producing the ammonia, you still run your compressor at 50% of its capacity.
Then it becomes more expensive.
At some point, it becomes more expensive to produce your ammonia, and that's also why you always want to have like a small buffer of hydrogen as well.
Yeah. Okay. So you have to take into account the whole plant, and probably a lot of that can also be a bit buffered with like hydrogen storage nearby, that you can smooth out this curves a bit, right?
Yes, but you would always want to make sure that the hydrogen buffers are not too big, because especially if you talk about a large-scale ammonia plant, if you would need days of hydrogen buffers, then that also becomes a quite significant safety risk. That's a lot of hydrogen storage on site.
Yeah, they consume a lot of hydrogen. And now that we have discussed the production of low-emission ammonia, what are the use cases that are now emerging from this low-emission ammonia next to like the conventional fertilizer production that we already have?
So let's start with that fertilizer production, because I would say that's already a very big market. Also, we have other markets like chemicals, explosives, also ammonium nitrates, for example. So you can decarbonize the current markets with the caveat that urea production might be a bit more difficult than the rest of the capacity. So there you could already capture process CO2 from the existing plants for about 45% theoretically of your ammonia plants for the non-urea capacity. Of course, also depending on CCS infrastructure or like electrolysis capacity scale up. But then the new markets that are emerging are the use of ammonia as a maritime fuel. So using ammonia to propel the vessels on the sea. So the second emerging market is ammonia to power and heat. So there's already some demonstrations for that in Japan, and I will get into that. And the third one is ammonia cracking, which from a thermodynamic point of view is a bit counterintuitive. So you're making hydrogen and then you're making ammonia, then you transport the ammonia and then at some location you crack it back to hydrogen. So as somebody sometimes called it, like you should be in thermodynamic jail if you do this. But somehow in certain jurisdictions, if the incentives are right, this might make sense. But I would also say that if you make ammonia and you can use it directly, that would make a lot more sense than, crack it back and then use it. Because every step basically costs you the cost of equipment, but also there is efficiency losses as well.
Yeah, definitely. It's though if you compare this ammonia, like hydrogen to ammonia to hydrogen to other hydrogen transporting options, then it's still favorable. If we want to transport it over very long distances, for example, from Brazil to Europe or from Australia to Europe, it's difficult to transport this renewable electricity. And for ammonia, since it's already such a big market, we already have the ships, we have the infrastructure for it. And that makes it then relatively easy to do that.
Maybe to add to that on already existing markets, so that's definitely true. We already transport something like 17 to 20 million tons of ammonia via the oceans. But also the vessels that are being used to transport the ammonia are actually the same vessels as LPG trade. So if we were going to expand the ammonia trade significantly in the coming decades, yes, we of course build new vessels that maybe also run on ammonia as a fuel on the waters, but you could also utilize your existing LPG fleet to scale up this trade of ammonia. So there's not that bottleneck. But what I already promised is to discuss a bit on the maritime and the power side. So on the maritime side, there have been quite significant activities in the past 2 years. So in September 2024, the IMO released the interim guidelines for using ammonia as a fuel in the vessels. So that is actually the first time that the IMO formally recognizes ammonia as a maritime fuel. So before that, it was kind of on a vessel by vessel basis, and you would need special permission to do it in a small tugboat or something. But now, from the middle of 2026, you're actually able to use ammonia as a maritime fuel.
Interesting.
And also use cargo ammonia if you're transporting ammonia in your vessel. And also in the same time, the engine vendors, they also developed these ammonia engines, and that actually went quite smooth. So the first of these these engines have been tested at the full scale for the performance. And what they actually found is when using ammonia as a fuel, it has lower NOx emissions than normal fuel oil mode.
Oh, okay.
And that was quite surprising, because everybody, when I came to a conference back in 2021, everybody always said, oh, well, if you're going to use ammonia, oh no, NOx is going to be very bad. Like every person on the internet who didn't like ammonia as a fuel, that was kind of their go-to argument. Well, now they shifted to other arguments because they don't win this argument anymore. But like, what they found is actually that the NOx emissions are 40 to 50% lower
compared to normal oil-based fuels.
Yeah. So that also means that if you build a vessel that is kind of ammonia capable, so if you build like the engine that could run on ammonia, it could also run just fully on fuel oil. Okay. So if you build a vessel, of course you need to supply systems for the ammonia, etc. But on the back end, the DNOx, you don't need a bigger DNOx for the ammonia. You could actually argue you need a smaller one, but you can just do it with that. So I think that was quite an eye opener on the maritime side. So that's going quite well. Of course, ammonia is quite toxic if there's an incident, and that also means that for the designs of the ammonia fueled vessels, there's really inherently safe designs that may not have been adopted before, but it also ensures the safety of the crew in general. So I think that's very good.
Yeah, but I think these ammonia handling, we already have a lot of knowledge from that, and now can apply these to other sectors like the maritime sector, and then make it a safe process because we already have so much knowledge about the handling of ammonia.
I would say that's definitely correct, but we should also be a bit cautious regarding that. And that is because the current industry that is transporting ammonia, handling ammonia, that typically happens in very controlled environments with trained operators. And if you look at, for example, the incidents with ammonia in the past, if you look at the fraction of the incidents, it's mainly refrigeration systems, small-scale refrigeration systems, and farm systems in the US. Because in the US, in the Midwest, some people use anhydrous ammonia directly as a fertilizer rather than urea or ammonium nitrate sometimes. And what you see is that really in these less controlled environments, that's where you get the people who maybe take a shortcut, like in the refrigeration system where they need to fix a cooling system or something, and that's where when the incidents happen. So I would also say that if you go to a new sector like the maritime sector, I think you also have to be very careful which segments you first address. Like if you're already transporting ammonia as a cargo, probably relatively low hanging fruit to also train the
Yeah.
operators to use ammonia as a fuel in the engine. But I would say that for each segment of shipping, you need to be very mindful of how you're going to train the crew and make sure that all the safety items are
Yeah.
in place.
And then also make it as straightforward as possible for these not so well trained people. Probably there have to be also more training involved when using ammonia compared to other fuels, but still it's a manageable risk, I would say. We have to use it with caution, as you said, but it's not this super uncontrollable dramatic risk.
No, and it's also a higher level of performance that you need, because if you have a small oil leak, like if you have a connection or a hose and it leaks a bit, well, it's of course it's economically bad because you're losing product. But from an operator point of view, it's a leak, and if it leaks a bit, well, too bad. But if you're working with ammonia, you will first of all smell it. It will not be very pleasant to smell it. I've been in a room where it was like 200 ppm. I cannot like, I do not believe people do that for fun.
No.
But so you need a higher quality standard on the things you're doing. So I think ammonia might also be this way of the maritime sector going to like a higher overall standard just because they need it for ammonia. But I definitely agree it's not, of course we should be cautious, respectful, but not
Yeah.
necessarily afraid.
Yeah, definitely. That sums it up very nicely. And what I think is also a benefit of this is that, well, when we use ammonia directly, for example, for power production, we can save all these conversion costs, but we can also become less dependent on these fossil production countries. That, especially at the moment, is also a huge problem because a lot of the ammonia is also coming through the Strait of Hormuz, which is currently making big problems. And with the electrolytic hydrogen and with the low emission ammonia coming from that, we can also produce that somewhere else in South America, for example, or Australia, somewhere where there's a lot of renewable energy, and we can more diversify our sources, I would say.
Yes, maybe to get to that current situation a bit. So the Strait of Hormuz, that's a lot of ammonia capacity that is also destined for, and fertilizer capacity destined also for the Asian markets. So that's, you talk about India, Japan, South Korea, for example. And quite often the ammonia trade is very much divided between west of the Suez and east of the Suez
Okay.
in normal times. So typically, that any capacity coming from there would not necessarily impact Europe directly via supply. But the issue is that when something is taken out of the global supply, basically vessels will reroute and serve customers that are willing to pay the highest
Of
price.
course.
So what you will see is that Europe, Japan, other rich countries, they still get what they need, but just at a higher price. But what you see is that the countries that cannot afford it will not get their fertilizer anymore, and then the harvests fail, and that's where you get these crises with food in these much poorer countries. So for me, when I see a Strait of Hormuz currently, I'm not thinking about like, oh no, the gas price in Europe is an issue. It's really like other regions where the countries do not have the economic power then anymore to buy the product.
Could these countries then also produce their ammonia domestically with their um, renewable energy sources, or is that still too far away because of also the economic power they need for that?
I mean, theoretically, yes. That would be like a very ideal situation, because once you put the investment there, it's a relatively cheap asset to operate, because you have the renewables. That's a capex investment. The basically the electrolyzer and the ammonia plant is a capex investment, and maybe the downstream fertilizer production also to a large extent. But the issue is that it's a lot of capex, a lot of investment. So when things like this happen, and also a few years ago with the Ukraine war, you saw everybody talking about like, oh, we need this local capacity, and then basically a few years are gone, and then everybody kind of forgets about it because the investment is so high. So that when I see these posts on the internet with like, oh no, we need local production, I'm like, yeah, very nice for the vibes, but like you need an investment of like hundreds of millions, maybe billions to build that. And it takes you like maybe 3 to 4 years to build that. I don't know how realistic like the short term gain is versus long term benefits.
Yeah, that's a good point. But I think it's also probably not to produce all of it domestically, but it's good to have at least some production capacity that you can at least have the minimal necessary amount of energy and also fertilizer, for example.
And if you look at, for example, a country like India, this is exactly also the strategy that they have. So they are currently one of the biggest net importers of fertilizers and also ammonia. So they import something like 2.4 million tons of ammonia per year. And what they now have is this SECI reverse auctions, where fertilizer off-takers in India will buy renewable ammonia from a locally produced fertilizer plant, so ammonia plant, sorry, renewable ammonia plant. So that's something like more than 700 kilotons of ammonia was being auctioned last year, and now they're finalizing those contracts. But their strategy is basically how do we replace the imports there, so we can serve our domestic market, and then also in the longer term, how do we become like a net energy, renewable energy exporter to the world? So indeed, you see that kind of narrative. And just to follow up then on my point that I promised to talk about a long time ago, the ammonia to power. So back in 2024, already Yara in Japan, they demonstrated 20% co-firing of ammonia with coal in a thermal power plant.
Meaning that you use coal and ammonia in the same plant to operate the generators.
Exactly. So, like out of the 1 gigawatt plant, 800 megawatt was produced via the coal input, and 200 via the ammonia, so to say. So it was mixed in the chambers, and it demonstrated this for 3 months with different variations of conditions just to demonstrate the technology. But what is quite interesting here is this is really a large scale, the largest possible scale you could have. And now they will actually also commercialize this and do this for real. So by 2030, they got this contract for difference by the Japanese government, which means is that basically the cost difference between the energy price from the coal and the ammonia price for the electricity generation, that's being compensated by the Japanese government.
How large is that different about like roughly at the moment?
Oh, it's very, very significant, because if you think about the process, is you start with ammonia, which contains a lot of energy, and then you go to electricity, which in a thermal power plant is maybe 35-40%, or maybe a little bit above efficiency, but also not much more than that. So basically, you destroy a lot of your energy to heat, which you're not using efficiently. So that's maybe not even the first thing I would think about from an efficiency point of view to use ammonia for power. But what I also feel like is today there is the demonstration with thermal power plants, but in the future there is also going to be combined cycle gas turbines fueled with ammonia. So I was in Japan last month, and I went to this site where they do all these demonstrations. It's very fascinating. So also the burners that we just talked about with the 20% ammonia co-firing, I actually saw the actual burners that they tested
Interesting.
at that site. And also they had like a 2 megawatt gas turbine fueled by 100% ammonia already on that site. But they also worked together. So there was IHI, and they also worked together with GE Vernova, one of these these OEMs for large-scale gas turbines. And actually, this week they announced that they did 100% ammonia firing for the F-class gas turbines of GE Vernova. And the interesting part for that is that when they get that commercialized around 2030, they could actually, instead of using these thermal power plants where they co-fire ammonia, they could build gas turbines on a combined cycle basis fueled with ammonia, which are much more efficient, maybe up to like 55-60% for ammonia.
That makes a huge difference.
Rather than this 35-40%. So you're throwing away less money when you burn the ammonia. If we look more at it like a European context, I would say Europe is, of course, importing less of its energy than Japan. And Japan also being a bit of a unique situation where there is also no nuclear power in the grid. In Europe, I think ammonia might actually play an interesting role as a peaker plant for the electricity grid, so on the long term. So if you really penetrate a lot of renewables into the grid and you also accelerate battery deployment, then you can do maybe like 90-95% decarbonization. But this last 5% or so, that's where you need to peaker plants, the backup power. So what I already alluded to in the beginning with my master thesis is you have this dunkelflaute in the winter where the wind isn't blowing so much and the sun isn't shining so much, and it's a terribly cold day. Everybody has bought heat pumps instead of their normal gas heated systems. So they will use a lot of electricity. And so for this last portion of your grid, that is where maybe you want to have like these backup gas turbine peaker plants based on ammonia that could then provide that last bit of green electrons.
Yeah, definitely. I think in this regard also the hydrogen peaker plants are also in the same context, and there it is, I would say, close to the shore where we would import ammonia. Then it's a no-brainer to use those ammonia fired plants. But when we are more like within where we have to transport also the ammonia somehow, then maybe it's worth to look at again to crack it and then use hydrogen pipelines. Or do you see also ammonia pipelines going through Europe?
Well, so that's an entirely different discussion. But first of all, the scenario you describe in the port area, it could make a lot of sense. If you look at, for example, Rotterdam, which is also a bunkering port for maritime fuels, where also probably ammonia will be fueled bunkered into vessels in the coming years. Then you can imagine that storage vessel that is also used to fuel these vessels via like a bunkering vessel, that could also have a pipeline to a gas turbine, a peaker plant running on ammonia. Because if you one thing to also consider, if you have a peaker plant, it's not going to run a lot of hours during the year. So if you just build a storage facility of ammonia, or also like in case of hydrogen, if you just build a storage facility just for a peaker plant, it's a very uneconomic investment because it's kind of a facility that you almost never use. So if you can tap into existing infrastructure in a port area, that makes a lot of sense. You can hook up to it. But then if you go more inland, maybe there are locations in chemical industries in Germany, for example, in the Ruhrgebiet, where there is already ammonia storage. So like these chemical derivatives of ammonia going via these barges of the Rhine today. So there it could make a lot of sense. But I totally agree with you. If there is a region where there is a hydrogen grid already and there is no ammonia infrastructure, it's maybe less logical to have an ammonia-fueled backup power plant.
Yeah, but that also what you just said with the ammonia tank, I think it's also relatively easy to store ammonia in like a tank compared to hydrogen, where you have to have a large pressure vessel, which has much other risks. And then if you really properly plan this whole situation, then it might be possible to, since it's not running so long, maybe for a couple of days, and then you can just supply it with the tank for like in place. But yeah, it depends on the usage.
That could be possible. And just coming back a bit to the pipeline, so the ammonia pipeline, I think that's technically possible. And also the ISPT in the Netherlands, they did a study a few years ago, basically what the state-of-the-art ammonia pipeline would look like. And there's all kinds of safety systems or like enhancements you could think about to minimize also kind of the exposure in case of an incident. So things like pipe-in-pipe designs or other safety measures. What I would say is if I look at the incidents with ammonia pipelines is that when they are very new, there's usually not an issue, but it's really the monitoring of the pipelines over time that is very important. If there's any, whether there's any cracks, whether there's any degradation, because you see in regions where there's maybe a bit less control on that, that's where the incidents happen after like 50 years or so.
Okay, so it's more to keep track of everything and then not have incidents later on. Interesting. Yeah.
Yes, and this can be like relatively stupid incidents where, let me tell a few stories there because it's quite interesting. So it can be excavation, for example, where people don't look at the map and then they bump into a pipeline and then, you know, like they have an incident. But if they did properly checked, there would not be this incident. But the second example I wanted to give is a quite interesting story. Because in some small village in the US, I believe it was, there was this kind of story that there was gold inside these pipelines. And then some kids believed that and they drilled a hole in the pipe.
Yeah.
So that kind of things can also happen.
Yeah, that's a very bad idea to drill into a pipeline. Still, also when it's there for a long time, then maybe people also forget about the risks a bit that come with the ammonia. And also you mentioned standards a lot. We are currently looking into standardization of all this ammonia infrastructure production and utilization with the standardization organizations in Germany. There's going to be a roadmap for that soon. And then we will look at what we already have, because we already have ammonia in the industry for a long time, and then we look into what new standards need to be developed to also cover all these new applications that will come from this low emission ammonia use.
And we have something very similar in the Netherlands as well, where a few years ago we had the update for the PGS 12. So this is for ammonia storage. So the last ammonia storage terminal was built a few decades ago in the Netherlands. And so when ammonia was being reintroduced as this kind of commodity that would be very relevant for the future, the first thing that needed to happen is to update the standards. Like, how do you build a state-of-the-art ammonia storage terminal? And what was very important in the Netherlands is that we used the polder model, where basically all the stakeholders get together. So it wasn't just industry. It was basically the permitting authorities, the government, the industry coming together, and basically together discussing the design that was allowable for everybody, appropriate for everybody. And with this, they also went out together and talked to local communities like, hey, it's not just a company that wants to build this project that is saying this is an inherently safe design, but it's also the permitting authorities who signed off on this. So, and that's kind of the narrative in the Netherlands for updating this. And also from a more global point of view, now there is standardization in the works on carbon footprinting of hydrogen and ammonia. And personally, I've also been quite involved with the ammonia portion of that. So last year we had some meetings with people from all countries around the world to also make sure that this aligns with the demands also from the different jurisdictions. Of course, this is a global standard, and all the countries and all the jurisdictions have already come up with their own rules in the past 10 years or so. So it will be very difficult to harmonize that anytime soon. But there is some standardization that is happening, so that's very good news.
Yeah, it's also very important in the case of ammonia for the acceptance that when people know that there are these standards that they can rely on, that ensures a bit more safety. And as you mentioned, also this whole accounting of emissions has to be standardized, because if we don't follow the same rules, it's really difficult to make an impact globally if some people just play with other rules, and then the atmosphere is for the whole globe. So we all have to basically pull on one string there to really make an impact, and not just Europe, for example.
And that's exactly the thing that I also mentioned about this the CO2 utilization. Well, if one company claims that that is a great reduction, whereas the another region in the world says this doesn't make any sense, then you quite quickly get into this discussion of greenwashing and that kind of things, and then people are very
Yeah.
upset when you get this kind of alarmist newsletters about that, and that's kind of what you want to prevent in
Yeah.
general.
Yeah, definitely. That's also a good point. And now we can come to the closing question, which is always, what is your favorite discovery in chemistry?
I think that has to be, of course, we talk about ammonia, so it has to be the Haber-Bosch process and everything that
Yeah.
came from it. Because it is such a fascinating kind of discussion also about personalities, about
Mhm.
discoveries that have come after it. Of course, the name Fritz Haber is a very important
Mhm.
figure here, but it's very important to also see what's kind of the person
Mhm.
behind that. Because Fritz Haber was, well, a very colored person. If I read
Mhm.
up on him, probably not the nicest
Yeah.
person in the world. Maybe I would slightly qualify him in some little bit narcissistic personality traits if I
Yeah.
read up on him. But what basically happened is that a lot of people worked on ammonia and other nitrogen fixation technologies, and many people couldn't
Mhm.
make it work. And also, what happened is that people worked on this, and this was high pressure hydrogen and nitrogen, and incidents happened in some
Mhm.
laboratories. So people stopped actually around some people around 1900. They stopped working on ammonia because they had a lab technician
Mhm.
dying. In some cases, it went a bit better, and Haber got this data on the thermodynamics, on the performance, and he said, "Well, this is going
Mhm.
to work." But then he came together to the meeting of the Bunsen Society, where basically there was a lot of prominent chemical engineers, chemists coming together, and they made fun of him because they didn't have the data that was
Yeah.
so good. So they made fun of him, and then his ego was very much trampled on, and then he was like, okay, I have to prove these people wrong. So then he went with his engineer Robert Le Rossignol, who was really the person making
Mhm.
the setup. So they tampered with the setup again. And then he had this Japanese person called Tamaru, who was very good at
Mhm.
measuring. And he came back with the numbers. And then that's kind of how this all spinned
Mhm.
out. Interesting story there is that Tamaru actually founded then Tokyo Tech in Japan. And that's still like a location, a university where a lot of the ammonia research in recent decades also has taken place. So there's still that heritage flowing from the Haber process into the global ammonia landscape. And to give an example, from the same group, there was this professor Kenichi Aika, and he was very instrumental in
Mhm.
ruthenium-based catalysts. And he has also been very instrumental in the Japanese program to actually get ammonia on the agenda for the demonstrations that we have today. So he was very like that's all very related. So that's very interesting. And then if you go from Haber, then you also had the material challenges. Like they never had such a high pressure
Yeah.
system
Oh.
in the world. So they had to design that. So the team of Bosch at BASF
Mhm.
got to work. He got also the Nobel
Yeah.
Prize for that work. They drilled a bit of holes in the in the converters to make sure some of the hydrogen would flow out, just to not have the
Mhm.
reactor blow up or have some other cracks in there. Then they have to make the catalyst. So Fritz Haber says, okay, we tried osmium, was an amazing catalyst. And they had no clue about how catalysts
Yeah.
fundamentally work. So Fritz Haber, for example, he came up with, well, we have to use uranium
Mm.
because osmium is a heavy element, so uranium must be a great catalyst. There was kind of the knowledge there. And then the laboratory at
Mm.
BASF, so that is the Alwin Mittasch and his people,
Mm.
they got to work and they tested basically the entire periodic
Yeah.
system. of
And he's
catalysts.
often
Of
forgotten in all
material.
these discussions. That is like Haber and Bosch, but in terms of the catalyst, Alwin Mittasch actually made great contributions.
Yeah, so what happened is that initially, like osmium was used in these demonstrative Haber. So the first thing that BASF did was buy up all the osmium reserves in the world, but that was like almost nothing. And one quote from the laboratories is that there's some kind of explosion, and Mittasch also said, well, if this is like, I don't believe it was Mittasch, by the way, who said it, but like somebody in the lab, they said like, oh my god, if this if this would have been osmium, this would have been the world resource of osmium that would have blown up. So they just tried everything, and then they were a bit lucky because they had this Gallifere magnetite from the north of Sweden, which is some kind of iron oxide, and it turned out to be quite
Mm-hmm.
active. And they really didn't know why back in the day, but in that iron ore, actually there is some potassium
Mm-hmm.
content, and that acts as a promoter for this breaking the nitrogen-nitrogen bond, and that made this such an active catalyst, where iron is the main active surface, but then you also need these
Mm-hmm.
promoters. But back in the day, they didn't know it, but they were just lucky that they put some random iron ore in it, and it was very active. The Germans then were very
Mm-hmm.
protective, and they didn't want to share any of this information, even after the
Mm-hmm.
First World War. So people, of course, knew they were making ammonia in Germany, and other countries were also developing this. But then the initial processes were very lousy in terms of catalyst performance. So they kind of had these iron catalysts that were like maybe a factor 10 less active than the
Mm-hmm.
BASF catalyst. So they had to eventually they found out what was the key ingredient, but
Took a long
um,
time.
but you really see that technology development, and it took all the way to the 70s and 80s with the work of Ertl and other people that we really understand the mechanism of ammonia synthesis and also the role as a
Mm-hmm.
promoter. And then he also got a Nobel Prize for that in the 2000s. So you see that there's kind of a decade, century of
Mm-hmm.
developments that were needed to make this
Yeah.
happen. So it has to be the Haber process that is the favorite
Yeah,
discovery.
definitely. It's also my favorite discovery, and it's still amazing. Although it's hundreds of years old, it still continues to be improved. And with all these new challenges that we also discussed today, with the flexible ammonia production, for example, and low emission ammonia production, it really stays a super interesting topic.
And the one thing that I would say is that, of course, we talk about many of these things as very new, but if you look back like 100 years ago, you had basically coal gasification for your hydrogen production, and you had water
Mhm.
electrolysis. So there was this book by Ernst from 1928, and it's a great book. It already describes basically the ammonia synthesis from water electrolysis, and then the other flavors you have for
Oh,
nitrogen
interesting.
fixation. And then if you look back now, I mean, it's very, very similar, kind of the options you have. Of course, there
Yeah.
is a lot of developments, but fundamentally, it's very similar again.
Yeah, super interesting. Yeah, thank you very much, Kevin, for this insights into ammonia synthesis and utilization and all your knowledge. I will link also the book of yours in the show notes, and yeah, maybe people get interested also in reading that from our discussion. Thank you very much.
Thank you very much. Appreciate it.
Also, thank you very much for listening. If you got interested in ammonia and all the use cases of low emission ammonia, you can find a link to Kevin's book in the show notes. And don't forget to follow Innovate and React on whatever app you are listening. Until next time, keep innovating and stay curious.